Hello everyone, and welcome back to Mitchell's Physics Review. Today we'll be working on momentum. Let's take a look at our problem. Two blocks of masses m and 3m are placed on a frictionless horizontal surface. A light spring is attached to the more massive block, and the blocks are pushed together with the spring between them, as shown in the figure below. A cord initially holding the blocks together is burned. After that happens, the block of mass 3m moves to the right with a speed of v 3m equals 2.45 meters per second. If we take a look here, we have our before and after diagram. Next, let's go to label our givens. Well, we know that the velocity of the 3m mass is equal to 2.45 meters per second, and we know that the change in momentum is equal to 0, which means the final minus initial momentum is equal to 0, which means the final momentum is equal to initial momentum. But how do we know that? Well, let's take a look at D to start. I know it's a little bit out of order, but this will help us conceptualize what we're going to do mathematically. So, at position A, neither one of the objects are moving, so they have 0 momentum as a whole. Then, at point B, when they're moving in opposite directions, we know that B is about 3 times more, has about 3 times the mass of A. So we have 3 boxes wide with 1 box to show it's moving at a velocity of 1 box, but it has a mass of 3 boxes. However, with M, we're going to do, it has a mass of 1 box, because this should be 1/3 of 3M, and we know it's moving about 3 times faster than the 3M mass. But how does this show that momentum is conserved? Well, it's a counting boxes game. So if you have 0 boxes to the left and 0 boxes to the right, then you have 0 for part A. If you have 3 boxes to the right, for instance, let's call right positive, then you have 3. If you have 3 to the left, then you have -3, which equals 0. These two are the same, which means momentum is conserved in the problem. Now that we know momentum is conserved, we can work on the mathematical portion of part A. So we know the final momentum is equal to the initial momentum. So from there, we can derive the equation mass times velocity of the smaller block, m, plus 3m of the velocity of 3m, the bigger block, is equal to 0. And then we know if we subtract to isolate Vm, we get negative 3m equals the velocity of the mass 3m. Finally, we plug in our given numbers to get the velocity of m is about negative 7.35 meters per second. Remember, because it's moving towards the left and we're calling right positive. Just like part A, before we start mathematically, let's take a look at the conceptual side. So, at part A, when the masses are still connected by the cord and the spring is compressed, how is the energy stored? Well, we know the energy is stored in the spring and not the rope. But how do we know that? Well, we know for the spring to be compressed, it has to have some energy. And this energy is from the 2 blocks that are holding it together. We also know that energy is some force over some displacement. So the force is from the blocks, and we know that the displacement is the how much the spring is compressed due to this force. So overall, we know that the energy is initially stored elastically. Finally, let's move on to part B, the mathematical side. So we already did this in part D, where we said initially all the energy is stored elastically. We know our system is the spring and the masses, and we know that at part B, all the energy is stored kinetically through mass 1 and mass 2 moving. We know it's not gravitationally because we're going to call this, the floor reference point, as 0. So it's moving along 0, so nothing gravitationally. So let's set up our equation. We know that the elastic energy is equal to the kinetic energy of mass 1 plus the kinetic energy of the second mass. We're going to just leave UEL like it is so we can find how many joules it is equal to. So for K1 and K2, we can start by replacing with our energy storage equations, 1/2 mv squared. But we can get a little more specific. We know the mass is just m for K1, which we're calling as this block. And we know the mass is 3m for K2, which we're calling this block, like we have denoted under the velocities. From there, we can plug in the numbers that were given. For this equation, we were given that the mass of m is equal to 0.41 kilograms. So we can plug that in for m, and this times 3m. We can plug in the velocity we're given for the mass 3m, and we can plug in the velocity we solved for in part A, vm. Then from there, we do the algebra, and we find that the elastic energy is equal to 15.03 joules. As you can see up here, those are all the right answers. Overall, what I learned from this process is to really have an easier time mathematically, start by doing the conceptual first. It helps a lot more knowing that momentum is conserved and where the energy is conserved and where the energy is stored initially, so that it's easier to set up diagrams and equations, making an easier solving process when it comes to the algebraic side. I hope you learned a lot from this too, especially about using diagrams and how important the conceptual portion to each problem is. Thank you.